Hi everyone and welcome to today's Chemistry Daily Booster. This is number 17 in our Paper 2 series and it is on the advanced information for both foundation chemistry and higher tier chemistry. What we're going to start off with then is understanding what an alloy is. If you're asked to define an alloy, we need to say it's a mixture of two or more elements where at least one is a metal. So there's two parts to this. We need to say it is a mixture of two or more elements, first part, and we need to say at least one is a metal, second part to it. There are 5 alloys you need to know. Now by know I mean know their names, know the metals that are involved, and also an idea of their uses. So steel first of all, the main metal there is iron, I hope we know that one, and this is what we use in generally buildings. Solder, that's made of tin and copper, and that joins electrical components. Brass, copper and zinc in musical instruments. Bronze, copper and tin in things like bells. And duralumin is aluminium and copper in aircraft parts. Now, one thing you may notice, if we look down our list, there is one thing that comes up time and time again. And that is copper. So if in doubt, as long as it's not steel, write copper for one of the metals if they ask you to. Because you can see there, in 4 of the 5 alloys you need to know, copper is there. The next best thing to do is, if you can't remember, write tin, because tin occurs twice. Obviously, you get a little bit of a hint in duralumin because aluminium and alumin, then you've got part of the word in there. The only one really that doesn't follow any real patterns is zinc. So just for our brass, copper and zinc there, just learn that one. But the others you can at least hazard a guess in a slightly intelligent way if needs be. Let's have a look at some of these alloys then in a bit more detail. So solder, as we've said, is used to join electrical components. Now, the good thing about it is it melts at just 227 degrees Celsius. So that means that when it's joining those components, it's not going to damage them. It's also going to be able to flow into gaps before solidifying. And of course, if we're joining electrical components, it does need to conduct electricity, which it does. If we consider the structure of an alloy then, what we can see on the left of this diagram at the bottom is pure copper. So all of the atoms are the same size, they're all held in these lovely, neat, regular rows, and therefore it's going to be quite easy to bend the copper. When we then compare that with the structure of brass, we can see these zinc atoms interspersed with the copper. Then what we've actually done there is it's kind of changed the arrangement. Because those zinc atoms are larger than the copper ones, they're not all sitting in these lovely neat rows, which means it's going to be much harder for the atoms to slide over each other. So that makes brass much stronger than copper on its own. Brass is also a good conductor of electricity and it will resist corrosion very well. In terms of our bronze, this is corrosion resistant and stronger and harder than copper alone, hence why we use it in things like our bells and our ship propellers, because we need something that's corrosion resistant if it's going to be sitting in the sea, for example, and we need it to be strong so that it doesn't bend out of shape. That leads us very nicely onto the idea of corrosion. When we talk about corrosion, this is just the reaction of metal with substances in the surroundings. If we think of some examples of metals that do not corrode, then we've got the unreactive ones, your gold, platinum. They don't react with stuff in their environment, therefore they do not corrode. Makes them brilliant in things like jewellery because they're exposed to a lot of elements you don't want them to corrode. Silver is another one that doesn't react easily with oxygen, but if we've got hydrogen sulfide present, then that does react with the silver. And what it does is it reacts with silver when the oxygen and the water are present, and we make this stuff called silver sulfide. And if you look at any silver items that have been sitting around for a while, so if you've got any silver things that people have in a display cabinet somewhere in your family, then they need to polish them, because if they just leave them, they end up with this almost black coating on it, and that is our silver sulfide. What we find then is we sometimes use this word rust or rusting to just describe corrosion of metal. That's wrong, because the only thing that we can apply the word rust or rusting to is when we're talking about iron, because rust itself is hydrated iron 3 oxide. So that's the name that we give to hydrated iron 3 oxide. We can't describe other metals as rusting because they're not hydrated iron 3 oxide. If we consider what rusting is, it's another redox reaction, so reduction and oxidation happening at the same time. And in terms of our word equation, this is it. Iron plus oxygen plus water makes hydrated iron 3 oxide. The problem with rusting is that once we actually create the rust, it will flake off the surface really quite easily. And every time that rust flakes off the surface, it then exposes new iron to the surroundings. Therefore, they will then react with the oxygen and the water, creating more rust, and so on until the whole thing is basically just corroded away. You can do a little investigation into rusting, which is what we can see in the little diagrams here. Usually there are going to be 3 different setups here. First one is air but no water. Second one, water but no air. Third one is air and water. And they can ask you to predict what you would see. Because we need oxygen and water for rusting to occur, the only one that has rust is the tube with air and water at the end. The others, there would be no rust. Because in this first tube, what we've got is this anhydrous calcium chloride that absorbs any water present in the tube. So there's no water to react, the iron will not react. In our second tube, what we've got is boiled water, so we've removed the oxygen. Again, we can't rust if there's no oxygen present. So no rust if there's no water, no rust if there's no oxygen, rust if both are present. So we know rusting is a problem. How do we stop things that are made of iron from rusting? Well, there's a range of things that we can do. Some things we will just paint, because paint creates a coating on the surface, preventing the water and the oxygen reaching the iron underneath. So painting is one way. If we're talking about moving parts, so think of things like a bike chain, for example, then what we'd actually do is coat it with something, oil or grease, or in other cases, plastic. Because again, as soon as it's coated with one of these substances, we're preventing water and oxygen reaching the metal, it will not corrode. 2 other options are versions of plating. We can plate it with zinc, so basically give it a coating of zinc, or we can plate it with tin. Now, what we actually find is if we need to write the half equation for rusting, then this is it. We start off with iron atoms, and then we're going to form the iron 3 ions. So Fe3+, and in order to change iron atoms to iron 3 ions, we need to also have 3 electrons there. One little pattern to remember here is when we're looking at the likelihood of metals to corrode, the more reactive the metal, the more easily it's going to lose those electrons, and so the more readily that substance is oxidized. So that means that the more reactive the metal, the more likely it is to react with the oxygen in the situation that we find ourselves. This is going to be important in our next bit. When we consider the process of sacrificial protection, this is where we are going to attach a metal that is more reactive than the one we want to protect to the surface. So quite simply, we can see it on the boat down here. We've got these little blocks of magnesium just attached all over this boat hull. The reason for that is that as long as that metal remains in contact with the iron of our boat, then the more reactive metal, the magnesium, is going to corrode first. So we're sacrificing that more reactive metal to protect the less reactive one that it's attached to. So just by attaching these little blocks of magnesium, we protect the underside of the boat there. because the magnesium blocks are going to corrode, the iron boat will not. Where we mentioned plating, then as we said, we're going to be putting basically a metal covering onto another metal to protect it. The whole way that works, it prevents the oxygen and the water from reaching the metal we're protecting underneath. If it's zinc, that's a process we refer to as galvanizing. So quite simply, you get whatever your metal structure is, dip it into molten zinc, lift it out, and then that will create a nice coating on the surface. A second option is we're going to plate it with tin. So here what we're using is electroplating, so connecting into a circuit so that obviously the tin is attracted to our steel. This is what we're going to use in food cans, for example. Now inside your food cans is a tin plate. So the majority of your can is just steel, but there is a tin plating around the inside. Now tin is less reactive than iron. So as long as that tin covering is in good condition, you're okay. However, if there's some kind of damage to the tin coating, what's actually going to happen is we're going to accelerate the rusting process for the iron, because iron is more reactive than tin, so to all intents and purposes, it's going to sacrifice itself to protect the tin. And that's the last thing we really want to happen, but that's what will happen. As always, if there are things you would like to look at in more detail from today's booster, head on over to the C6 playlist on the channel. Use your revision guides, your classwork notes, and of course have a little look at some of the paper 2 chemistry papers in advance of your exam. Just gives you a bit of a feel for the kind of questions that come up, and those questions that come up over and over and over again. Then don't forget to join us again tomorrow for our next daily booster.